Good day to everyone. So in the last video, we have discussed about the hydrostatic pressure and how this pressure is affected the objects inside the liquid or a fluid, and we have also discussed about the Pascal's principle and how this Pascal's principle is applied in various applications. So we have studied that the pressure which is acting on the point P. Suppose if you consider a point P and the pressure acting on this point P, which can be written by the mathematical notation with a small area, which is given as dF divided by the dA. So dA is a small area and dF is the force acting on the small area dF, which can be written by this mathematical equation: pressure is equal to dF divided by dA. So that the total force extracted on the by the liquid column on the whole of the area in contact with this liquid is called as the thrust. That is nothing but the total force, which can be written as pressure into the area it is acting. Okay, so the thrust can be written as the total force exerted by the liquid column by the whole of the area in contact with the corresponding liquid. Therefore, if you consider the liquid which is at the rest position, always exert a thrust normally to the surface in contact with its object. Now we are going to find out this thrust of the liquid on any immersed plane. Suppose if you are to consider a water tank and if you are placing any object inside this liquid with some height h, and what is the thrust acting on this corresponding object, which we are going to see, and we are going to derive the mathematical expression for that. Suppose if you consider the tank, and the tank is filled with the water, and this is the surface of the water, in which above this is the air. This is the contact part of position of the air as well as the liquid. And if you consider the small immersed plane inside this liquid, which is actually situated from the height of h from the liquid surface, and the area of the immersed plane is taken as A, and the density of this liquid is taken as rho, then the pressure at any point in this plane is actually uniform, because the plane is actually in position horizontally in position with the surface. So that means every point in this plane is actually equal height from the surface, so that the total pressure acting on this plane at any point is uniform, which can be written as P, which is equal to h times of rho into g. The h is the height of this plane which is situated from the water surface, rho is the density of the corresponding liquid, and g is the acceleration due to gravity. Now I can write the thrust which is acting on this horizontal plane, which is written as the pressure multiplied by the area, the total area. This is equal to P into the total area is A. So I can write it as A, so that I can just substitute the values of P in this here, so that I can write the thrust as h times of rho g into A. So therefore, this thrust is actually acting on this immersed plane, which is actually immersed horizontally in the liquid, and each and every point of this plane is experiencing the same pressure as well as the same thrust. Suppose if you consider the same object, same plane, suppose if it is not actually in a the horizontal position, suppose if it is in the inclined position, suppose, so then there is the each and every point in the plane is actually having the different height from the surface. That means the total pressure which actually vary with respect to the depth of this points inside the liquid surface. So the correspondingly the thrust will also vary. So now we are going to find out what is the thrust of this immersed plane. Suppose if it is actually positioned in some inclined position. Now let us consider the same water tank and the same immersed plane, but instead of it is actually placed in a horizontal position, now it is actually immersed with some inclined angle, which is actually taken as theta from the liquid surface. So we must first determine the thrust on the surface, the thrust on a small area of the surface, and then we can integrate to the whole range of the plane over the entire surface. Suppose if you consider a small area of this plane, which is having the area of dA, which is actually situated from the height of h from this liquid surface, and the distance from this inclined angle from this point to the point which we have, I mean, the area which we have considered is actually taken as x. Then the thrust acting on this small area can be written as, so the thrust which is taken as a df, because it is actually acting on only small area, which can be clearly written as h times of rho g into dA, that means the total area. So you can write there that the thrust acting on this small area dA is equal to df is equal to h times of rho g into dA, where the h is the distance of this small area from the liquid surface. Now, if we consider the distance of this the small area from this liquid surface is taken as x, then then we can write the sin theta as sin theta. That means this angle and can be written as sin theta is equal to h divided by x, or I can find the height actually, which is equal to sin theta x into sin theta, right? So that I can just substitute this height into this thrust equation. So the df will be equal to x into sin theta into rho g times of dA. So this is the small thrust acting on the small area of dA. So that if you want to find out the total thrust, that means the total force acting on the entire plane, then you can just simply integrate this equation, so that I can get the total force, the force, when the total thrust as F is equal to integration of x sin theta rho g into dA. Here the except this x into dA, all the other values are constant, so that I can just take it as outside. So sin theta rho times of g x into dA, because the x is actually vary. Suppose if you move this area in this direction, similarly the area, the small area will also vary. Suppose if you are increasing from the from one point to another point. Therefore the total thrust F, which is equal to rho into g sin theta of this x into dA. Here we can note that this x into dA is nothing but the moment of the element at the point of dA. So x into dA, which is nothing but the moment of the element, moment of the considered element dA of the surface of the liquid from the surface of the liquid, that means the surface of this liquid surface. Therefore this integration of x into dA is nothing but the moment of the area, the moment of the whole area of A. So the moment of the whole area can be written as the integration of x into dA, which is nothing but the A times of capital X. So this capital X is nothing but the distance from this liquid surface to the center of gravity of this corresponding element. Suppose if this is the center of gravity of the center of gravity of the corresponding the element, the plane we considered, then the x is the distance from this point to the liquid surface point, that is taken as the capital X. So the distance from this point G to the liquid surface is taken as the capital X, that is nothing but the multiplied by this area of the element we have considered is the total moment of the corresponding area. Now if you substitute this value of xdA in the value of xdA into this total thrust equation, then the total thrust can be written as F is equal to rho g into sin theta into A into x. And if you are considering this center of pressure is actually situated, center of gravity is actually situated from the liquid surface is taken as capital H, that is the distance from this distance from the liquid surface to this center of gravity of the element, then that is taken as a H. Then I can find out this theta value from this point. That means from this point to I can find out the theta value for this center of gravity, which can be written as sin theta, which is equal to H divided by the capital X. So that I can just substitute this sin theta into this equation. The final answer will be H is equal to rho G H divided by X into A into X, so that this X and this X will be get cancelled. So the final answer will be F is equal to H into rho G into A, which clearly shows that this H times of rho into G is nothing but the pressure which is acting on the point G. That means that this point G, the center of gravity. So this is the total the pressure acting on this center of point, and with the area of the total area of A. So the F is equal to the total thrust can be written as the H times of rho G into A. Therefore, I can written as the total thrust, the resultant thrust on the immersed plane which is equal to the pressure at the center of point, center of gravity, multiplied by the area of the plane. Now from this equation you can clearly find that the thrust of the total thrust on the immersed plane is quite independent of the angle of the inclination, which is theta, with the liquid surface, but it is only depending upon the total height as well as the area of the corresponding the immersed plane. So now we have obtained the resultant thrust acting on the immersed plane. So our next step is we have to find out the point of the plane in which the resultant force is the pressure is acting on the entire plane, which is called the center of pressure. Okay. So as we already know that, suppose if any object is actually immersed in the liquid surface, there is a pressure is acting on this object, which is actually normal to the corresponding object. Suppose if we consider this as immersed plane, and this pressure acting on this immersed plane is actually directly normal to this the plane, so that the total pressure is acting every point is like this. So each parallel line is actually equal to the H times of rho G into dA. That is, this is force acting on the particular point, particular area, which is having the area of dA. So we can therefore now determine the center of these parallel forces, that is the point through which the resultant force is acting on the entire plane, by using the principle of by applying the principle of moment, which we have considered, which we have calculated now. I mean derived the equation now. So the principle of moment is nothing but the algebraic sum of the moments of the system of parallel forces above, which is acting on this plane, which is acting on this plane about an axis, which is equal to the moment of the resultant force about the same axis. So the moment of the thrust or force is actually acting on the area dA is actually, we have just derived this expression as H times of. So the moment of the thrust H times of rho G into dA acting on the small area of dA about this liquid surface can be written as, so the moment of the thrust this is equal to H times of rho G into dA multiplied by the distance x, or we can write this equation just by substituting the values of H. So we know that H is equal to x times of sin theta, so that I can just substitute this value into this equation. So I can write this equation as rho times of G x times of sin theta dA into x. So I can just again rearrange this. Just find the final equation of the moment of thrust as rho times of G x squared sin theta into dA. Therefore, if we can just consider the total moment of the forces acting on the whole area, then we can just integrate this equation. So the total moment of area, the total moment of thrust this is equal to the integration of rho g x squared sine theta into dA. So obviously we know that there is rho g and sine theta is constant, so only the total moment of thrust is actually we get depending upon the rho g sine theta integration of x squared into dA, where this integration is actually extends over the entire surface of the corresponding plane which we have considered. Now if you look into this equation, this integration of x squared into dA, which is nothing but the geometrical moment of inertia, which we have studied. Studied this into the unit 2 when you are studying about the elasticity, which we can write as I times of g. So that is the geometrical moment of inertia, which is actually the area of the A of the which is about the about from the liquid surface, so that the total moment of inertia can be written as, so the total moment of thrust can be written as just substituting this the integration of x squared dA instead of Ig. Just substituting this integration of x squared dA to Ig, so that the total moment about the liquid surface, which is equal to rho times of g sine theta into Ig. And we already know this Ig is nothing but the geometrical moment of inertia can be written as Ig it can be written as A times of k squared, where this k squared is nothing but the k is nothing but the radius of gyration. So the k is nothing but the radius of gyration, which is actually depending upon the shape of the material which we are actually immersed into this plane. So I can substitute this value into this equation, the total moment, which is equal to rho times of g sine theta into A k squared. And again, if you consider the another point in here, suppose the total resultant force acting and the parallel lines acting on this surface. Suppose this is the point where the center of pressure is actually, that means the total resultant force acting on this point is actually situated here. Suppose if you consider this is the point which is taken as a P, and the distance of this P from this the liquid surface is taken as, so the distance of this point P from the liquid surface is taken as a capital S0, and the height of this height is actually taken as, that is, this point is actually situated from this liquid surface is taken as a H0. Then the resultant thrust about this liquid surface can be written as, so the resultant thrust about the surface, liquid surface, which can be written as the total surface into the distance x0, so that I can just substitute the f times of x0, which is equal to the resultant, the total moment of the total moment of the thrust, which can be written as rho into g sine theta into A k squared. So which will be equal to this the resultant thrust, so that I can from this relation I can find out the values of x0, which is equal to rho g sine theta A k squared divided by f. And this f we already find it out is nothing but the capital H times of rho g into the capital A, so that I can substitute the values of f is equal to H times of rho g into capital A, which we have previously calculated, so that I can just substitute this equation, this relation here. So rho g sine theta A k squared divided by H times of rho g into A, so that this rho g and rho g will get cancelled and A will cancelled. The final value of x0, which is equal to the sine theta into k squared divided by H. Or if I write this, H is equal to x times of sine theta, from the sine theta equal to H by x, so that I can find out the capital H is equal to x times of sine theta, and I can substitute this value in this equation. So instead of the H, so x into sine theta, so this sine theta will cancelled. The final value of x0 is equal to k squared divided by x. And if you consider this, suppose if you consider the k0 is the radius of gyration, of the area which is actually parallel to this center of gravity. So it is of derivation about the center of gravity. Then according to the parallel axis theorem of this moment of inertia, I is equal to written as I0 plus a times of x squared. So this is the moment of inertia with respect to the parallel axis theorem, the principle of parallel axis theorem, and the I0 is the moment of inertia of the about the axis through the center of gravity. So that I can substitute the values of I and I0 here. That means I is nothing but the ak squared, which is equal to a k0 squared plus a x squared. So I can just take the a as a common in both the right hand side as well as left hand side. So the cancelled out each other. So k squared, which is equal to k0 squared plus x squared. And if you substitute this k squared value into this equation of x0, then I can write the equation of x0, which is equal to k0 squared plus x squared divided by x. So from this equation, you can find out the x0, that is nothing but the center of pressure of the x0 is nothing but the center of pressure of the center of pressure point from the liquid surface. And if you look into the equation for the center of pressure of the equation, x0 is equal to, which is actually depending upon the geometry of the corresponding material which we have used. Suppose if the geometry of the material is different, that means if you take the rectangle or a circular or a triangle, then the center of pressure of the corresponding geometry of the material will be different. So from this equation, we can easily find out the center of pressure of any lamina, rectangular or a circular or a triangular lamina, using this equation, which we have seen in the next class. Okay. So if you have any doubts, then we can discuss in the online class. Okay. Thank you.